an introduction to optical communication networks. In this introduction, we discussed the development of the history of development. And we said that initially, optical communication networks were limited capacity, and we saw the two reasons. Can anyone remind us of the two reasons why initially optical communication was limited capacity?
Lack of sources, light sources.
Yeah. Yes, okay.
That's one.
That's good. And the other one? Security is an advantage. So it was one of the advantages we discussed at the end of the lecture. But now we are talking initially in the late 19th century up to the up to the mid of the 20th century, optical communication systems were of low capacity. One reason it was the lack of suitable light sources. The other is
amplifiers. Use of amplifiers.
yeah, this came as a later milestone. But initially, it was the lack of light sources and the fact that in free space links, the communication is limited by line of sight. And light is affected severely by the atmospheric conditions. Then, the invention of lasers and the proposal of the use of glass-made fiber as the communication medium for light came as the major step towards the optical fiber communication networks we have now. Okay. Then we plotted, if you remember here, a plot diagram of an optical fiber communication system, and we tried to identify the different components, and we also discussed the different options for modulation and the different options for detection. Can anyone remind us? What did we say about modulation? Direct modulation, external modulation, and for detection, we talked about. You had 2 weeks, so I expect that you will spend some time. And if you don't, you'll really struggle by the end of the semester. We talked about coherent detection and direct detection. And we said in direct detection, we detect the level of the power. No information is carried in the phase. So the light in this case is incoherent. And we call this direct detection because we are actually only counting the photons. And we said that there is another option which is coherent detection, but we will not discuss that. We will limit ourselves throughout the course to direct detection, and which always has to come with intensity modulation. Because we said we only count photons. We do not modulate the phase or the frequency. So that's why it always comes with intensity modulation. Okay? So throughout the course, we'll be always talking about intensity modulation, direct detection systems. Okay. Then we talked about the propagation of light in optical fiber. And we said that light propagates in optical fiber as a result of total internal reflection. And we talked about the structure of the fiber. Snell's law and the total internal reflection, refraction, all these. Okay, and we talked about different types of fibers. What were the types we talked about? Okay, and what's the difference between them?
And the single one just allowed to pass through only one beam of light.
Ray or moon, yes.
And it has a small diameter.
Yes, multiple, larger diameter, it allows more. Yes, and we talked about the limitations of the multi-mode that led us to develop the single fiber and also other variations of the multi-mode fiber. to eliminate dispersion. What was that?
Sometimes if you if you have multiple light beams, they might arrive in different times. So
Yes.
the final solution for that is to have them in a curved way
Okay.
with different refraction
Yeah,
indices,
and,
so they can arrive at the same
And
time.
what did we call that type of fiber?
Eukaryotic
Hmm?
fiber.
Yes, okay, you're reading from the sheet. Where is index fiber? Great, okay. And we discussed the main transition characteristics of optical fiber. We discussed two main characteristics. What were they?
High value,
Hmm?
high value, the laser attenuation.
Yes, okay. And for attenuation, what were the main sources of attenuation?
In multiple absorption, inside optical fiber.
Yes. And the other source?
Interference. Scattering.
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 Okay. And we had a long discussion and we ended up saying that the absorption was reduced to a very low level, that the main source of loss is scattering or Rayleigh scattering. Okay? Creating this window of low loss frequencies, which gave us the three windows for optical communication, which are what are the three windows? Centered around which wavelength?
1.5.
Yes, 1.55, yeah.
3.32.
Hmm? 1.3 and 8.8. And the most used are 1.3 and 1.5, and the preferred is the 1.5. Do you remember why we said the preferred one is 1.55? Because of optical amplifiers. Okay, and we will discuss that later in 2 lectures. Okay. So this was about the loss. What about the bandwidth? We already mentioned something that affects the bandwidth. Dispersion. Yes, and what are the types of dispersion?
Material dispersion.
Hmm?
Material dispersion.
Material dispersion. Okay. Hmm? Regular voice?
Based on impurities, the material and the impurities.
Okay, before we go into detail, I think we are more talking now about the absorption. Okay? Absorption, we have the intrinsic and extrinsic absorption, and the extrinsic is because of the impurity. Okay? So for dispersion, we said we have two types of dispersion. Chromatic intermodal dispersion, and this is what we were just talking about when we discussed single mode and multimode. And this can be eliminated using single mode fibers, or we can get rid of 99% of it with the graded index. Okay, the other type, unfortunately this is not the only type, the other type is chromatic dispersion. And there are two types of chromatic dispersion: material dispersion and waveguide dispersion. And we found this interesting fact that they cancel each other at a wavelength of 13 or 1.3. Okay. Yes, it's one of the windows, but we are more interested in the 1.55 window because of the optical amplifiers. And that's why we came up with dispersion shifted fibers. And then we discussed also other variations. There were some limitations with this zero dispersion shifted fiber, and then we had the non-zero, and then there came the flat dispersion fiber. Finally, we discussed or we compared the advantages of optical fiber communication to other communication networks, copper-based and satellite and the others. So we had that list of advantages. Can anyone mention one or two of the advantages? The main ones?
Passive.
Hmm?
It's a passive medium.
Sorry?
Passive, it's passive.
What is passive?
Optical communication. The advantage, is that what you want? Like,
Okay, there are some components can be passive, but others are not. Okay. Obviously, the main advantage is the increased bit potential for bandwidth. We have other advantages like improved security.
Less
It's-
activation.
Yes,
Less activation.
yes, and we said that the optical fiber within 10 years of the invention of optical fiber, the attenuation of it was lower or became lower than the attenuation of copper. Okay, so now I've spent considerable amount of time reminding you of what we learned last lecture. Because this is really important that you understand the physics and the reasons why optical fiber is the great communication medium we have now, and it's facilitating our lives, bringing us this huge internet bandwidth. Okay? Today, we will look at direct detection receivers, or in particular the noise in direct detection receivers, and the performance of analog and digital transmission under quantum noise. So we'll start with direct detection receivers. Okay, we said we will limit our discussion to direct detection receivers. And in direct detection receivers, we just said that we count photons. We just care about the level of optical power. Okay, and a direct detection receiver is made of, we had this from last week. A photodetector, which can be a photodiode PN junction, EIN junction, or avalanche photodiode, followed by an amplifier, equalizer, and then the decoder. It's important that the detector, followed by the amplifier and further processing circuits, perform well together. Okay? So, and the major performance parameter that we care about is noise. So what is noise? Noise is, as you all know, is any undesired disturbance that masks the signal. Any disturbance that will not allow us to detect the sent signal. Okay. This noise is important because it imposes performance limits on the receiver. Limits in terms of the minimum optical power the receiver can detect. Okay? Means that if the received signal is lower than this minimum optical power, then it will not be detected. And we refer to this as sensitivity. Okay? Noise in optical receivers is different than noise in copper-based systems. They both have thermal noise. For optical fiber receivers, we will also have to consider the noise in the photodetector. And in the photodetector, there's two types of noise. dark current noise and quantum noise. So we'll spend the next hour, or the next hour, the rest of the lecture discussing these three types of noise and the limitations or they impose on the system performance. Okay? So this thermal noise, you must be familiar with thermal noise in your previous study. Thermal noise, they also refer to it as Nyquist noise or Johnson noise or Nyquist-Johnson noise, is the random fluctuations in electrons in conductors at room temperature. So we all know that conductors conduct current because they have atoms that are not tightly bonded to any of the atoms. They have electrons, free electrons, which are not tied to any atom. These can move freely, and if voltage is applied, they will conduct current. Okay, even in the absence of voltage at equilibrium, still these electrons can fluctuate, or they can be thermally excited. This is what Nyquist has described to us in his formula as the mean square value for the thermal noise is equal to 4K, where K is the Boltzmann constant, T is the absolute temperature, B is the post-detection electrical bandwidth, and R is the resistance. Okay, it was implicit from my discussion now that this happens in a conductor, but maybe I didn't say explicitly that this is concerned or thermal noise happens in the load, in the resistor load of the photo detector, because it happens in a conductor. Okay? These fluctuations are random. You cannot, it's impossible to predict them. So that's why we give the thermal noise in terms of its mean square value. So we can see that it's proportional to the temperature and also proportional to the bandwidth, which will mean that we will have to achieve a trade-off between the bandwidth of the receiver and the thermal noise, which is also the case for the dark current we will see shortly. Okay? So thermal noise is the noise generated over or across the load resistor of the photodiode. These fluctuations will appear as fluctuations in the voltage across the resistor. And this will be added to the voltage resulting from detecting the photons. And that's why we say thermal noise is additive noise. Okay? Which being added to the current resulting from detecting the photons means that it can lead to false detection or can lead to an error. Okay? Is that clear? So this is the first type of noise we have. The second type is dark current noise. Dark current is the current we have in the absence of illumination, when no photons are arriving. This can be due to background radiation entering the system, entering the device, the detector. But this is not a problem in the optical fiber. It's a problem for free space links. So in optical fiber, we neglect this background radiation. The dark current we are interested in is a small reverse leakage current flows through the detector, flows through the receiver. Okay, this is mainly attributed to thermally generated carriers, electron-hole pairs. Just to make it clear for you, or to make sure we understand this clearly, let's try to remember. Can you all see here? So the photodiode is a PN junction. So we'll have here the depletion area, depletion region. So this depletion region will create a voltage barrier. So no electrons will flow, no current will flow. When we have a photon incident to the detection area, this photon will be absorbed by any of the electrons, and then it will transfer to the conductor's layer, creating an electron hole there, which will soon be drifted to the edge of the depletion area and then to the terminal of the devices, resulting in current. Usually the PN junction the voltage barrier created in the depletion region is supplemented with a voltage reverse bias voltage to make the depletion area larger, so we can detect more photons. Okay, so we agreed that no current will flow unless we have a photon. But actually this is not the case, because still electron hole pairs can be generated thermally. And in this case, we'll have an electron hole pair that will be drifted to the terminal of the devices, and we'll have current flowing. And this is the dark current we were talking about. Okay? Dark current, because it's resulting from the movement of discrete particles, and in this case electrons, it manifests itself as shock noise. So what is shock noise? Shock noise is the fluctuation around the average value that results, as I just said, due to the movement of discrete particles, in this case electrons. This shock noise was defined by a German scientist called Schottky, and this is not the case, it was called shock noise. It was called shock noise. Actually, when he first defined or identified this shock noise, he was working on vacuum tube. Okay, and if you bring headphones and put them across a PN junction or a photodiode, and they have done that, and you try this is at no voltage applied or reverse biased, okay, and you try to listen, you will hear this shock noise as if it's bullets shooting on a metal. So that's why they call it shock noise. Okay, so it's like something hitting a metal plate or something. Okay. Schottky, it's easy now to remember his name, defined the dark current, or the mean square value of the shock noise, as 2 E, which is the electron charge, B, the bandwidth, and I is the DC current. And for us here, for the dark current noise, it will be 2EBID, where ID is the dark current we just discussed. Okay? Dark current is, as we just said, is generated or is proportional to temperature, so it can be reduced by cooling. Also, it is related to the width of the depletion region and the material of the device. So by controlling all these elements, we can reduce the shock noise. So why shock noise is a problem? Why dark current noise, which is here shock noise, or in general shock noise is a problem? So we said it's fluctuation around the average value. Okay, I'll leave this point when I come to the next slide to make it clear for you. Okay, let me say it now briefly and later we will discuss it more. So why shock noise, or why these fluctuations are important? Okay, when you have a large flow of electrons, high current, these fluctuations will be very small, that they will not affect your system or your decision or whatever. But in this case, we are detecting very few electrons, very few photons, which will result in very few photons, very few electrons. So the current is really small. So any fluctuations will be really significant. Okay? And we'll talk now about an example which will make it clear. Question? Yes, please.
Yeah, just to confirm the difference between the small ID and the big ID.
This is
shock noise.
dark current noise.
This one.
This is the noise, the fluctuation.
And
this
that
is
the current.
the current itself, the DC current. Okay?
Sorry.
So
The square is noise or the...
no, this is the noise. And because as we said with the thermal noise, it's something that it cannot predict, it's random. So that's why we define it by the square mean value. Okay? Clear?
So that's the noise and that's the dark current. They're two different things.
Yes, this is the dark current noise, this is the noise, the fluctuation, this is the current itself.
Okay.
So this is, so you will have dark current, which is the function of temperature and voltage, and it has a certain formula which we are not interested in. Okay? So you will have a DC dark current. There will be fluctuations around the average value. The dark current itself, you can calculate the value of that. As I said, it's a function of voltage and temperature. Okay? But these fluctuations are what cause the problem, because we cannot predict them. They are random. Okay? Is that clear? Should I go forward? Okay, quantum noise. So, quantum noise is the noise associated with the fluctuations in the photons hitting the photodetector. The detection of light in a photodiode is a discrete process, since the creation of electron holes is indicated by the photon arrivals, and the later is a discrete process. So we have the current generated from the photon arrivals, and this is a discrete process, as the photon arrival itself is a discrete process. Okay, and it was found that So we are sending 1 and 0s, and we expect a certain average value for 1 and 0, maybe no photons sent with no illumination during 0. So there will be fluctuations around this average value. Consider, for example, this laser pointer. I'm pointing to the wall, hitting the wall. Okay. There will be certain number of photons hitting the wall, and the average number determines the brightness of the light. Okay. The physics that resulted in generating the photons from the laser is random in time. So photons are generated randomly. Okay? Because billions of photons are generated to create a spot of light. Fluctuations will not be a problem, as we just said. But if we reduce the number of photons, reduce the brightness, which means reducing the number of photons, then the fluctuations in the number of photons hitting the wall will impact the brightness of the light. To make it clear, the experiment of tossing a fair coin. Okay, if you repeat this, the experiment of tossing a fair coin for 1,000 times. Okay, if you repeat this for many times, the expected outcome will be 50% head and 50% tail. And if you do this for 1,000 times, if you toss the coin 1,000 times for many times, okay, the outcome will slightly fluctuate over the average, which is 50% heads and 50% tails. But what if we repeat this experiment for a limited number of times? Then the outcome will significantly fluctuate if you just repeat it for 5 or 10 times compared to the 1,000 times. So these are the fluctuations we talk about. And these fluctuations become significant when the number of experiments, when you toss the coin, or the number of photons traveling to hit the detector is limited. Okay? It was found that the probability of detecting Z photons in time period tau when it's expected to detect Zn photons obeys the Poisson distribution. So we expect that on average for a bit of 1 to detect 10 photons. Okay, this is the average. The probability of detecting Z photons, anything different from this average, follows or obeys the Poisson distribution. Clear? Should we go forward? An important concept, very high, an important concept that we should familiarize ourselves with is the quantum efficiency. Quantum efficiency is the ratio between the generated electrons to the received photons. In an ideal system, each photon will result in generating 1 electron. But this is not usually or always the case. Okay. So RE is the rate of electron. So it's electrons per second. Here it's rate of photons. So this is photon per second, and this is electron per second. Okay, the number of photons is basically the received optical power, or the rate of photons, so I say the rate of photons is the received optical power divided by the energy of the photon. Do you agree?
Isn't that rate of electrons? Isn't that rate of electrons, not photons?
Sorry. Okay, I was saying photons, but I meant do you agree?
Divided by the frequency, what is it? So the power of photons is divided by frequency of what?
This is the energy. Oh, the markers. This is the energy of the photon. H, the blank, constant, and F, the frequency. So this is energy of photon. So as you said, you are counting photons. So the total power we receive, we divide it by the number of photons, by the energy of photons, we will get the rate of photons. So this is in joules per second, and this is in joules per photon, which makes this photon per second. That's why it's a rate of photons, not a rate. Is that clear? Sorry, the markers are all not good. Anyone with markers by any chance? Clear? So yes, so we can use this to find the number of electrons generated, which is the electron efficiency by the, sorry, I keep saying number, no rate of electrons generated, the quantum efficiency by the rate of photons. And the rate of photons, as we have just calculated, is P naught. Okay? So this is the electron rate. And if we want the number of electrons in a certain period, we just multiply it by the time. So we get number of electrons. Yes. When we will look at this now and become
Is this still on? So this one
Yes.
the unit, electron per second.
Yes, electrons per second, as we have written here.
So when
Where
it has,
electrons per second, yes.
so when it has the time period,
This is when we want the number of electrons.
it's still
Hmm?
this is still like this is unity second time.
Ah,
So this is unity like of the
so
second to time period. It's still
there should be here tau missing. Thanks for spotting this out. Thanks a lot. Okay. So this should be something like this. Number of electrons, what do you want to call it? Ne is equal to Re, the tau, which will be to be more accurate. It's very essential that you can understand all the concepts we have discussed so far to be able to go forward in the next session. So any question? Last time you were more active asking more questions.
We had a day.
Huh?
We had a day.
So now we know, okay, thermal noise, dark current noise, and quantum noise. So now we want to study the impact of, or the performance of analog and digital transmission under quantum noise. So we said that noise is called limits in the performance. This limit is in terms of the minimum energy the receiver can detect. And if the signal is lower than this energy, it won't be detected. It will be masked by the noise. And we refer to this limit as the receiver sensitivity. Okay? This sensitivity in analog systems is, or in digital systems, or starting digital systems, is dictated by the bit error rate. While in analog systems, as we will see shortly, it's dictated by what? In digital systems, we have bit error rate in analog signal to noise ratio. Okay. So first, we'll start by considering the digital system, digital transmission. Okay. We make a number of assumptions, which should be clear for you. We assume that the receiver is ideal and it has, or it's followed by an amplifier that is sensitive enough to detect even the displacement of a single electron hole pair. Okay? So even if a single photon, alright, single electron was generated, because when we say idle receiver, this means what in terms of what we just discussed, the quantum efficiency. It has 100% quantum efficiency. And 100% quantum efficiency means what?
Ideal.
Hmm?
Ideal. Like every photon generates an electron.
Yes. So you have one photon, one electron. So in this system, we have every photon will generate an electron, and we have an amplifier that can detect even this single electron. Okay? We assume that the receiver is, or the photodetector is ideal or is perfect in terms of that it doesn't generate any electron hole pairs in the absence of illumination. Okay, means that if no photon is incident, no current will be produced. And we also neglect dark current. So what does that mean? Just think of these two. Any photons that comes, and okay, it's something to make it clear for you. Here we consider that during for a 0 bit, no illumination, no light is sent off. Okay? So think about these two. And what do they mean in terms of your system?
No loss.
Hmm?
No loss.
No loss? Loss is what we discussed last lecture.
Yeah, but like if it has a high quantum efficiency, then
Oh, you mean, okay, every photon is translated into
Yeah.
an electron.
it's more
Okay,
efficient.
and photons only arise when we have a 1, when we are transmitting 1. If we are transmitting 0, no photons will arrive. And this guarantees for us that no current will be generated in the absence of light. Okay? Which means that, is it possible that we send 0 and we detect 1? No, it's impossible with these assumptions. Okay? And this is what we say here. No false alarm errors or false alarm errors are ignored. Okay? So this is a result of this system.
So from dark current, change the 0 to 1 or
No dark current. Here, yes, if we have dark current, yes, it can change 0 to 1. Yes. That's why we are concerned about it. Okay? So no dark current and no other sources of current ever in the absence of illumination. Which means we cannot transmit a 0 and detect a 1. So this error is not possible. Okay? And what did we say? Okay. The only error possible in this system is the probability or an error can only occur if a light pulse is present and no electron hole pairs are generated. Okay? So we said P. Can I erase this? So the probability of detecting 1 while a 0 is transmitted, we said this is not possible with the assumptions we have. probability of detecting 0 while a 1 is sent will be the only error possible in the system. So then this will represent the error of the system. Okay, and this will give the bit error rate of the system, PE. Okay, this probability, according to what we just looked at here, we said that this process has Poisson distribution. So this probability is equal to what? Just substitute. What is that? Z is 0. And Zm? Okay, Zm is the number of photons that corresponds, the average number of photons that corresponds to 1. Okay, so this is the average number of photons that we expect to get. Okay, then this will be equal to?
E to the power minus.
And you understand what is this the Zm is the number of photons that we expect to detect when a 1 is sent. Okay?
I have a question.
Yes,
So,
please.
the O1, like the switch from like O to 1 or 1 to O.
No, this
Or what does
is
it mean? Like
this is the probability that 0 photons detected while a 1 is sent. And what does 1 sent mean? It means that we were expecting while Zm is expected. This Zm number of photons, average number of photons for a 1 bit. So when we send 1, we have illumination. We transmit light photon. When we send 0, we don't transmit any. This is the assumption for our system. Okay. So in this case, we transmitted photons with average number of Zm, but we detected nothing. 0. So if we go back here, to the Poisson distribution, and we try to apply this, Z for us here is 0, and Zm is the number of photons that we, the average number of photons that we expect when we send the 1. Okay? And as Z is equal to 0, then this probability is e to the power minus Zm, and we said this is the only probability of error possible in the system.
So we can avoid this sentence. Yes.
This is the only probability of error in the system. So it will give the bit error rate of the receiver. Okay? So now we'll do an example, or okay. Now we'll do an example where this Zm is used to identify the minimum energy the system can, or the receiver can detect, which we refer to as the quantum limit of the receiver. Okay? Should we go? Should we go for the example? Okay, so spend a minute reading the example. You are not interested in the example? So a digital optical fiber communication system operating at a wavelength of 1 micrometer requires a maximum bit error rate of 10 to the power minus 9. So let's write down. So they are telling us that the wavelength is 1 micrometer, the bit error rate is 10 to the power minus 9. They want us to determine the theoretical quantum limit at the receiver in terms of the quantum efficiency of the detector and the energy of an incident photon. We said, what is the quantum limit? It's the minimum energy the receiver can detect given a certain bit error rate. We said that bit error rate is e to the power Zm, and this was given as 10 to the power minus 9. So from here, we can obtain Zm as 20.7 watt. What is the unit of Zm?
That's photos or photos per second?
Because remember what we were saying here? This is the number, average number of photons we are expecting to be made. So from this Zm, how can we figure out the quantum limit? Go back a few slides back, and you will find that we have defined here the number of electrons. And the number of photons. We said here the number of photons, we wrote this here, or the rate of photons is the optical power divided by the energy of the photon. Okay, and this will give us the rate of the photons. Okay, and we want the what we want is the optical power. So what can we do? Zm, which is R number of rate of photons over a certain period is equal to can you all agree with this? This is what we have just obtained a few slides ago. Okay? And what do we want here? At the quantum limit, which is the minimum energy. The minimum energy is what here? Hmm? The minimum energy of the signal. So it will be detected given this error rate. We want the energy. P. P is the power.
Each times half. Each half.
Wait, I start telling you because I'm hearing lots of answers. What is the energy?
HCC over
Hmm?
HCC over
You want to say that this is the power?
Yeah.
Why?
Wait.
Wait. What? I think you are not getting what we are trying to obtain. Yes, that's correct. That's very correct. We will come to your answer now, but first I want you to understand what we are trying to get. What we are trying to get is the minimum energy of the signal received, so that we will detect it correctly given that bit error rate. So HF is the energy of a single photon. Okay, but we have many photons. We want the energy of all these photons. Okay, and this gave us, if you remember, the rate of the photon, the power, incident optical power over the energy of the photon. So we had the rate. Okay. So if this is the incident optical power, and this is the time period you are considering that that the power is incident over, then this will give us the energy, as your friend there said. So then this is the quantum okay. So we can see the minimum energy.
Excuse me, can you say again why quantum limit is equal to P times tau?
Quantum limit is the minimum energy. You understand that the minimum energy that we should receive to be able to detect the signal without error, given this error rate. Okay, so we are looking here at the energy of the signal. We have got O as the power of the signal, so we just need to multiply by time.
But in the previous equation, you say HF is equal to energy of the electron, so we are confused.
No. HF is the energy of the photon, one single photon. And we are using it here when we want to identify the photon rate. So we got the whole power divided by how the energy of each photon. So we get the rate of the photons. Now we are not interested in a single photon, right? Now we are interested in the incident power that we were given at the beginning. Okay, so if this is incident power, this is the incident power that will result in this number of photons. If you want the energy, so just multiply it by time. P naught or PO here, whatever, tau. Okay, so this will be Zm HF over the efficiency. And we have Zm as 20.7. Yes. And HF over the efficiency.
Can you raise the total?
Just I don't want it to get to the light here. Here. H is the lag. Are you with us up to here?
Yeah.
Okay, so just do the math. E to the power Zm is equal to 10 to the power minus n. So you can get the Zm. Do the math. Okay? H is the Planck constant, and F is the frequency, and you were given the bandwidth, the lambda, the wavelength. So we can do this as 20.7 H C over lambda. If you want in terms of okay, and if you want the value, you have everything here except the quantum efficiency, and which we will later. But in the question they say in terms of the quantum efficiency and the energy of an incident photon, okay, which is this. So actually, we don't need to give this. This is the energy of an incident photon, and this is the quantum efficiency. So this is A of the question. Okay. B. The minimum incident optical power required at the detector in order to achieve the above bit error rate when the system is employing ideal binary signaling at 10 megabits per second, assuming the detector is idle. So what information are we given here? So we were told that first the detector is idle. What does that mean? It's ideal. Yes, so the quantum efficiency is equal 1. And we were given the bit rate as 10 to the power
56.
Now we want the optical power. So what we want here is P. Okay. So to be able to obtain this P, we will need what? Given this formula, what is it? This formula, yes. We wanted the energy, so we took this together. Now we want the power by itself. So then we need the period, the time. And in the question, we were told that, there's something here. Ideal binary signaling. An ideal binary signaling has got 50% ones and 50% zeros. Okay, so we can assume that this power is sent over 2 bits, a 1 and a 0. And as we said earlier, in this system, we assume that zero, no light is sent, no illumination during 0 bits. So then the period here for us will be the period of 2 bits. Okay, so from here, let's say so then this makes tau equals to what? Remember we were given this. 2 over. Okay. And then just a matter of substituting the values. And so let's write here from this equation, let's call it 1. From 1, P naught will be equal to Zn HF over
Excuse me,
yes.
I'm still struggling about what do you want to say about IP signaling, like 50%. So the rest of the
I did means 50% ones and 50% zeros. Okay, when you have streams 1 0 1 0 0 1 1, 50% ones and 50% zeros.
Because the ideal binary.
Huh?
Because the ideal binary.
Yes. Now, an ideal binary signal means that the resulting stream will have 50% zero and 50% one.
So it's obviously for our not.
Sorry?
Twice too much. So we just put 1 0 and 1 more.
Yeah. It's because we assume or we consider here that there is no energy transmitted over a 0 bit. Energy is only transmitted over a 1 period. A 1 bit when we want to transmit 1, we'll transmit light. 0, no light. Okay? So then this will be over a period of 2 bits. So it will be 2 over the bit rate that we were given. Okay? From 1 bit, yes, and which is equal to, and we have everything. We have Zm, we have H, Planck constant, F, we have got the wavelength, the quantum efficiency is 1, tau is 2 over bit rate. Okay? And the value for this, if you do the calculations, will be 20.6 pico watt. Usually the power is expressed in dPs, relevant to, want to express it relevant to a reference power level of 1 watt, then it will be what do you say? So P naught is E naught over P some P reference, and if we have P reference as 1 watt, then P naught, to do the calculation, it will be minus 146.9 dp watt, and if we want to express it in dpm, then P naught in dpm will be 10 log P naught over P reference, and this P reference is 1 milliwatt. And if you do the calculations, this will be minus 76.9 dpm. This is how you usually express the power. Okay, so these are the values. This is the power in terms of watt, power in terms of dp watts, and power in terms of dp. Okay, that was the question. Let's have a break. Let's have a break. We are not left with lots of time, but we need at least 5 minutes.
She always power.
So we'll be back by 5:30. No, not 5:30. Sorry, 5:25. 5:25. We are scared. We will be back by 5:25. Yes.
Slide 28.
Slide.
The ones I have here, they don't have numbers. So what's the title of the slide?
The one that had the